So I'll catch up this weekend. So I know a couple of you mailed me some capstones and stuff, and I need to respond to, but I've been swamped. So, so finally this week I got it unburied out of my project that I was way behind on. It was a big finite element model that I was, trying to incrementally, like programming, trying to incrementally build it, and luckily on Tuesday, it did start to work. And it's like any kind of piece of code, finite element models the same way. You've done nothing until it actually works. How code is like okay. And I try to build code or models incrementally because I used to work with field programmers, and they would always make like 20 changes, and then it wouldn't work, and it'd be well, which one of the 20 was it? So I'm always real careful trying to make one or two changes at a time, especially when I'm building a finite element model, because if it blows up, then I at least know where it blew up. And so anyway, Tuesday my model finally worked, and so really basically yesterday was when I first started, because I had to add another couple of parts. Yesterday was when I first started really getting results out. So, and I was really worried about that project for myself. So anyway, so I'll catch back up with my email this weekend and everything. But so anyway, this chapter today is very interesting. It's an extension of what we did on chapter 4. Chapter 4 we were doing just the factorial experiments, and it's been 2 weeks. But remember, that was where we had multiple factors, and maybe we had 3 things that were varying, and 2 levels in a couple of them, and 3 in another, and so our approach in chapter 4 was just to make all possible combinations and test them all. And remember, we had to at least test twice at each combination, 2 or more, so we could get an error term. Otherwise, how can you possibly come up with any error term if you're not comparing the same thing at least once? And so, but that was the case where we were happily and luckily could make all these combinations and do all these tests without the concern of a background variable. We could do them all at the same time, they were quick, or we could control all the background variables, and life was good. Well, now we've got the problem where that's not so. We've got so many combinations, or the test takes so long, or there's so much stuff going on that we've got a background variable that's bothering us. So in chapter 4, we might have had, we might have had factor 1 in our table going down this way, different levels. We might have had factor 2 over this way, going down the columns. And then maybe that was it. Or maybe we had a third factor, when we repeated it. So maybe we had another set of columns over here, factor 2, A, factor 2B, and then maybe factor 2 of the list here, and then this is factor 3 here. Factor 3 in these blocks. Okay, well now instead of doing that, so that was chapter 4, so now instead of doing that, we've got these blocks, and this is going to be background variable 1, background variable 2. Okay, so and the reason we're doing this is because we've got some background thing that, like time or batch or something, that we can't filter out. We have to recognize that it's a problem. It's messing up our data, and so we're going to split it up that way, which I know looks very similar, but we're going to treat it a little differently. Looks similar to this 3-way ANOVA that we did last time, but we'll treat it differently because we'll treat these as background variables that we can't control, and we'll roll them in to the error differently. So now what we'll do is learn how to treat this in a couple different ways. This is a very short chapter, but it's actually got a lot of stuff in it. And so what we'll do, I'll show you how to do an ANOVA based on this. Unfortunately, of course, Excel doesn't have it built in, nor does the real stats. But I've got a paper, and that's part of what the notes are, shows you how to do it by hand, and that's how I've done it. Now, but I don't stop there, because one of the things we've always said, you always heard that old saying where, if you got a hammer, then everything looks like a nail. And we've got ANOVA and statistics, and everything looks like we need to apply a two-way, a three-way, and a million-way ANOVA. That's not true. And so I'm going to show you another way to treat these things in what I call the engineer's approach, where let's just fit them all and subtract, or account for this background behavior. Go back to our same old way of processing. Why not? I mean, there's nothing wrong with that. We don't have to always use these statistics tools just because they're there. I mean, I know statisticians want to do that, but there's nothing wrong with making your own little correction for days and accounting for days, or correction for batch and accounting for batch, subtracting that out or adding it in or whatever, and then going back and just treating it as a two-factor thing or something. And so I'll show you that using the example they've got. I'll do it their way, but I'll do it with an Excel sheet by hand that does all the ANOVA calculations by hand. Then I'll show you what's wrong if you did it wrong. If you did it like without accounting for the background, I'll show you that. And then I'll show you this other approach, what I call the engineering approach, where we don't just have to rely on the ANOVA, we can account for these background variables with the model and subtract them out and get an answer, and get the same answer. And I mean, I shouldn't say the same answer, not numerically exactly the same. We'll draw the same statistical conclusion. And so that's the direction we'll go. And so even though it's a short chapter, it's got some good depth in it, and it's a nice treatment of a multi-factor with background variables. And it's also got a little part in it on where we go ahead and use Sheffy's technique again too, back from chapter 3. So I've got that rolled into the notes too. So I think it'll make sense. And I think again, remember, we're building on things. We started way back with everything was hunky-dory. We had no blocks and just one factor, and then we added two factors, then we added background variables, then we kind of reversed and went back to where we could mix and match everything, but we had 3 or more factors. Now we've got multiple factors, but we can't quite mix and match things because of background variables. But one of the things we do have, I think they used the word right away somewhere in the chapter, complete. Complete on page 108. It's complete because we were able to fill in every spot. Okay, so we were able to do every factor and under the same background conditions, and over here every factor under the same background conditions. It's going to get worse. We're going to get to where, we got some holes in there, and because time or constraints or the data you have is incomplete. That's for later chapters. So right now this is complete. We filled in every spot, but in this chapter we don't have any replications in each spot. We'll deal with that too. So that's where we're headed. That's where the chapter fits in the progression of things. And again, I want to encourage you. You don't just because we have these tools, you don't have to take this approach. There are other ways to do things, and we'll show that too. So let's see. So the caveat or the assumption is we can't do complete randomization. And remember, complete randomization is meant just that, any subject could fall anywhere because there were no background variables. It didn't matter. You could take subject A and test him over here and subject B over here or whatever. So, but for some reason, we can't do that because there's some background variable. And remember the book, and we keep saying the background variable is quite often time, but it might be like that water example, source, or it might be, I guess they had time in that one too, had multiple sources and they had time, or it might be, manufacturing process, and it's a batch, material batches. I got this one batch, I can do this set of tests, but now I've spent a month doing these tests. Next month we got a new batch of raw materials, and I just can't account for that. And maybe it does, maybe it doesn't matter. That's where you're going to have to know, and that's one of the things. The takeaways from this kind of class is, when I take tests, when I do experiments. In fact, I brought one of them. I actually am like an old-timey dude. I get the bound lab notebooks, and I wind up writing everything in it. This is one that we're using. In fact, I've got a trip next week. I'm taking it with me. But I even write weird things that I think might matter, but I'm not sure. Because you never know when you're going back and analyze the data. What was that background variable that bothered me? I write down the serial numbers of the equipment so that if I go back and set the experiment back up and something seems weird, well, maybe I used, one oscilloscope or one amp one day, and the next time I didn't, and maybe I need to go back and actually repeat everything exactly. And I know they told you to do that back in, chemistry lab, but it's actually the right thing to do, because you've got to be able to distinguish these background variables, and they may matter. They may, and depending on, right, you could be ridiculous, writing down everything, the color of the sky and that sort of stuff, but hopefully you know your process well enough to know, well, this background variable doesn't matter, these do, and I don't know about these, but at least let me try to record them. So I would encourage you that to be one of the takeaways too. So anyway, so what do we look like? Well, remember before, we've always had our total variation, and we're always busting it up into the treatments, because that's what we're looking for, and the random error, which is what we can never get rid of. And we may have, 2 treatments or 3 treatments or 4, depending on the setup. We may, if we have more than one treatment or more than one factor A or factor B or factor C, if we have more than one, then we also perhaps have the interaction between A and B, or A, B, and C. And remember, and we talked about first level interactions, A and B, or higher level interactions where we had, A, B, and C, those kind of things. But we've always had that, and now we're adding some variation that's a result of these blocks. Okay, and the variation is a result of the background variables. And remember, our statistical objective is always to either minimize things, like minimize random error if we can, or if there's things we can't minimize. I mean, by minimization, the best thing to do is not have these background variables. Yeah, great, I wish I could do that. Or if we do have to have them, maybe we can at least control them. If it's time, well, maybe we can at least take the data at the same time of the day under the same conditions, those kind of things. But if we're stuck with it, which we often are, and we can't minimize it, or we minimize it as much as we can, then if we can't get rid of it or minimize it even more, let's at least explain it. Because you'll see from one of the examples today, if you don't explain it, if we don't throw this and have these blocks and attribute some of the variation to the blocks or the background variables, then if we can't do that, then it just falls into this block, right? If it's something we can't explain, either by understanding the background variables or we just don't know, then any of that error, those calculations that show up in our, our magic ANOVA, and when we push the button, well, if we don't know that these blocks exist, this is all just going to pile right down in here. And remember, if it piles down in here, remember our whole statistic is this big F that we keep coming back to and loving on, the mean square error from the treatment divided by the mean square error from, this is the random part. And if we keep piling these numbers and values down in here, then this gets big, which means that gets small, which means we just can't plain see what we're trying to find. Well, remember, our goal is I think our goal anyway, is to observe that one or more of the treatments is doing something. I mean, you occasionally have the opposite goal, which is, I'd like to prove that none of these things matter, but that's just as bad too. If you make this giant, you're always going to conclude they don't matter, which is a stupid mistake too if they do. And so if we're trying to shrink that down to as small as we can get it, so that we've got some statistical, accuracy or some precision, right? If we make this big, we just blast it away. We've got to have, the treatments have got to be huge differences to make this F get to be 2 and 3 and 4. And remember, again, we're always comparing this calculated F to this F distribution that, F equal to 1 is not important, and we're always comparing it out here to some F critical, or we're looking at the probability that you got out that small. So getting F big means the treatment did something. Too big a thing in the bottom, it won't show up. So our goal with this setup and our goal with the mathematics is to be able to explain this so that it doesn't fall in here. Because now it's okay. If we can explain it and it's part of the block, then great, it's part of the blocks. And guess what? When we do our ANOVA, it'll show up that the blocks are significant. Well, whoop-de-doo, didn't you already know that? Yeah, because they're background variables, and if you hadn't thought they were significant, you wouldn't have put them in the background. You would have just lumped them all together. So you know, coming up with an F on the blocks, well, yeah, okay, the background mattered, but that wasn't what we were looking for. You know, we're looking for the F here or the P here to try to understand what our process is doing. So, but we'd like to throw, if there is some variation or error or whatever that's cause of that, let's put it there. That way it doesn't muddle this up and make it too big. So that's why we have these blocks. That's why we do the math the way we do. So from the design of experiments approach, like we said, well, what can you do? Well, we can control the background, right? Eliminate it if we're lucky, okay? But okay, we probably wouldn't have this chapter if we could always control backgrounds, right? We just always control them, okay? Or we can manipulate our background and just do all the treatments at once. Again, okay, that's nice in the fake world, but it's not possible because maybe it takes too much time, or you know, we need multiple batches, those kind of things. We can compensate for the background by fitting a model to it, doing a regression. That's what I'll show you. That's my engineer's approach rather than doing the statistical approach. Or we can do the statistical approach and account for the background with this blocking approach in ANOVA. So we got 4 things we can do from a design and experiment perspective. Yeah, don't have backgrounds, okay, I love that. Or do everything real fast so we don't have backgrounds, or do everything with one batch so we don't have backgrounds. Compensate for it with a model, or account for it in the statistics. Oh, okay, that's good. We got four ways to handle this issue with backgrounds. And then maybe we'll discover that the background didn't matter, and okay, that was good. We learned something there too. So let's jump straight into the book. The book has a nice example. So it's got a chemical process, and they've got temperature and pressure affects the yield. I think it is, yeah, they call these just yields. I think that's all they call it, right? Yeah, just call it. They're not saying really what it is. Alrighty, so you've got 4 different pressures, up to 200 to 275, with 3 different temperatures, low, medium, high. And then we couldn't get all the tests done in a single day, so we had to do them on a different day, and we've somehow believed that day matters, whether it's humidity or the batch, or maybe there's a different operator or something. So somehow we think that the day is a background variable. And so we've got our factor 1 and factor 2, our block 1 and block 2. So the days are the blocks because the day or time is our background variable that we're worried about. Temperature and pressure then therefore are our treatments, right? That's what we want to know. Does temperature and pressure change the yield? But we've worried about the fact that day is a background. So let's see, how many treatments do we have in each of the blocks? 12. 3 temperatures, 4 pressures. So in their nomenclature, they've got a K is their number for the number of treatments, N is the number of blocks. So we'll see that in a minute. So let's see. Again, a comment about the data here. We don't have any replications, right? We didn't take 2 values at that temperature and pressure like we kind of were doing last time, so we could get an error term. So already you might be saying, well, you know, where are we going to come up with this? So maybe we'll do a little of the math, and then we'll say where it comes from. We kind of may remember where it came from, sort of from last week, but let's see. So if you look at the total variation, because you know that's what we're always worried about. What's this total variation? We're going to bust it up into blocks and treatments and random. Okay, let's see. Did we do that mathematically? Yeah. The total variation. Remember, the SS was the sum of the square error. We're always doing this sum of the square, so we can negative and positive cancel. So we got 3 parts. Yeah, just like the diagram. So the total sum of the square error is 3 pieces: the blocks, the treatment, and the random. Remember, treatment's what we're looking for, and treatment might be, treatment A, B, and C, but we'll put them all in one right now, or here we'll split them up down here, right? So, and remember the error. Well, that's the part we can't get rid of. This is our new part that we're hoping now to be able to account for,
so that it doesn't become here, right? Because if this is a big question mark, if we don't understand it, well then, okay, it just, those two roll together, the unknowns. All right, so let's break our treatment up. Well, we have, in this particular example, we have a factor A and a factor B, and we also have whatever error is caused by their interaction too, that might exist. Okay, so we've got the block, factor A, factor B, the interaction, and the error. So let's see, what does the block look like? Well, like before, let's if we want to discuss the error as a result of a block, well, yeah, let's just look at the block mean and compare it to the grand mean. Remember, the grand mean was everything averaged. The block mean would be, okay, it's average, right? Yeah, let's see, we're going to average over all of the things in one treatment, and we're going to average over all the things here. Take the difference, square it. Okay, yeah, that'd be for a single factor, right? And then you can again look into the math. It doesn't bother me that you don't have to know all the details, but you can. I don't think it's hard. Looking at which indices you summed over. Remember, the dot was you completely summed over that index. So so for two factors, let's see, what would we be doing? Right, we would take this one, you would sum over everything, right? Yeah. And then here you would sum over all of the A's and B's of in a particular block. Yeah. Yeah. And so you could continue on with the math in there, but again, I think the details are fine. So if you did an ANOVA, let's see, from Minitab, let's look and see what it looks like. So this is just straight out of the book. And then I'll also recreate this without using Minitab, although I am going to get Minitab and bring that into class. So let's see. So what do the results look like if we selected that pile of data as it was laid out and had Minitab and ran an ANOVA? Okay, we get this spit out here. Let's see. A little fuzzy, but let's see. So here, what pieces show up in it? Well, of course, everything's going to show up in it, right? You've got the block, you've got the factor A, which is temperature, factor B, which is pressure. You've got the interaction of temperature and pressure. We've got the random error. So we had every piece that was in that equation. The total is made up of each of these. Remember, they each have a degree of freedom. Remember, the degree of freedom is always one less than the number of levels you have. So the degree of freedom of days is 1. We had 2 days. Temperature, we had 3 temperatures, so the degree of freedom is 2. We had 4 pressures, so that's 3. And then you can figure these out from each other. And we can look at the sum of the square errors. That are the simple, straightforward calculations. And in fact, this particular class, I'll show you how to do those exactly by hand. Then the mean squared error, which was that divided by that, which is this is the guts. This is what we're trying to dig out, and then your F, which is related to the mean square error, or your P. Now remember, we can always take the F, compare our F, when we find our F, this part. So when we find our F out here, F calculated, and so we can either compare F calculated to the critical value at 5% or whatever we want, or we can compare this this P, either one. Remember, it's always the statistical test. Are we looking at, is F bigger than a critical value, or is P smaller? An F critical would be calculated, say at 5. Yeah, there. So your F critical will be at whatever level, the 5% level, the 1% level. You choose that. That's your statistical significance level. So then P will be either compared to 0.05 or 0.01, which again, that's your level you're choosing. All right, so let's look at these P's. Yeah, they're fuzzy. So this one was 0.001, I think. In fact, right with them, I guess you can see it. Let's see.
Well, it's in the book too, so it's table 5 too, so you can't see it on there well. So that's, yeah, the first piece, 0.001, the next is just flat out 0 to 3 decimal places, the next one is 0.009, and the last one is 0.979. So what do these conclusions mean? Well, 0.001 is far less than 1%, far less than 5%, so that says, yeah, the days mattered. Well, I would hope that we would come up with that conclusion if we thought days were background. So, but if not, maybe our conclusion would be, oh, gee, we goofed up. Days weren't background. Days did matter because P is really small. And that's the equivalent of saying it was really statistically unlikely that this would happen just by randomness. Because it can, right? You could randomly do some bad experiments, change the days, and it could happen. But, well, not with this low of a probability, right? It's very unlikely. Temperature, whoops, it mattered for sure. It was 0, 0. And look, their F's are huge. Pressure was 0.009. That's less than 1%, certainly farther less than 5%. Pressure mattered. The product of temperature and pressure did not. You know, almost 1. So it didn't matter. Now, if you wanted to know where these P's came from, this is the Excel command. F.dis.rightTail with the F value and the degrees of freedom from the numerator and the denominator. Remember that mean square errors in the denominator? Yeah, that's what we've always been comparing it to. The numerator is whatever thing you're asking the F about. I put treatment in that little write-up because we were talking about treatment, but here the numerator is the day. Here it's temperature, here it's pressure, here it's temperature times pressure. It's F distribution right tail, the right tail, right side, that's why. And why is it F dist? Well, just remember, the distribution gives you the probability, the inverse gives you the F. So if you had a probability and you want the F, well, just F inverse right tail. Okay, and this is the F value, and those are the degrees of freedom, numerator first, denominator next. So for example, this one, 27.17, a 1 and 11, a 2 and 11. I'm sorry, I can't read my writing. 2 and 11, 2, 11. In fact, you'll notice 11 is always in the bottom, right? Because we're always using MSE as the denominator. And then, you know, this one had 6, that one had 3, and so that's part of the reason why this one got so darn big. It had 6 degrees of freedom up there. So we running this ANOVA, just selecting the data, and if we were fortunate enough to have many times, running this ANOVA, boom, it spit out, it gave us the answer. We found that day mattered. We already knew that anyway. Temperature mattered, pressure mattered, and temperature times pressure did not matter. Okay, nice. Now we could go further with this, and we will in a minute, because maybe some of the, you know, this only told us that one of the temperatures mattered, at least one, and at least one of the pressures mattered. They all might not have. You know, remember, it just tells us that there was a difference. But if we didn't tell us which one, we have to use those Sheffys or Tuckies to further dig into it, or we can look at graphs and things like that. I mean, we're not in the dark. We don't have to just run the ANOVA and say, oh, that's it. If it doesn't come out in the ANOVA, I don't know. We can look at the graph and see. Why not? Look at the data. Think about it some. Okay, so this is nice because they had Minitab. So what's our problem? Currently, well, our problem is our nice low-cost stats apps that I keep pushing on us, Excel and Real Statistics and even MATLAB. They don't do this thing the two-way with the blocks. So okay, so what can we do? Well, we can redesign the experiment so we don't have to do this. Now, yeah, get rid of the background of blocks. That's always an option, right? We can buy a Minitab, which I'm going to do here for us in the next week. We can learn R, which is R is free. You can do that too if you want to. Or we can do it by hand. Yeah. That still lets us use Excel. Yeah, let's do that. So if we're going to do this by hand, we need to know the math that's going on in the ANOVA. Well, that's okay. We can do this. Remember, these ANOVAs, although the tabular results appear like, wow, what went on in there? It's not hard. We're just adding up a bunch of numbers and squaring them and taking the difference and dividing by, you know, some degrees of freedom. That's pretty simple math for Excel. Pretty darn simple math. The only thing these nice little add-ins do for us is they've done all that for us and put it out in a nice pretty table and let you just select things and stuff. We can do
We can do that for a data set this big, which for a lot of us, that's all we're going to have. So, you know, hey, let's look at it. So what does the math look like? Well, some people, nice statisticians and all, have, you know, boiled this down to some nice, simple things, approaches to do some of these sums of the squares a little bit easier than just beating it out the hard way. And so I found one from Lincoln University in New Zealand that shows you how to do this quite efficiently. And I've got the paper in here. We'll look at the math on my notes, then we'll look at their little paper real quick. So let's see. So remember in table 5.2, the one we just looked at, the answers, we had several sum of the square errors, didn't we? We had a sum of the square due to the block. We had one from each of the treatments, the temperature and the pressure. We had the sum of the square of the combination, temperature times pressure. We had the sum of the square error and the sum of the square total. Right, I gave them the name. You got block, factor A and B, interaction between A and B, the random error, and the total variation. Okay, and this, you know, if we have three things, temperature, pressure, and, you know, volume, well, we just have another one, factor C. Now we got more interactions, AB, AC, BC, ABC. Okay, but that's all right. So this New Zealand group looked at the math, played around, and has come up with some intermediate sums that are useful to us. One's called this correction factor, and one's called the sum of the square all. So let's see what these are. And the paper also has it. So let's see. This correction factor thing is sum of all of the entries. All of the entries in the data thing squared divided by the total number of entries. So the total number of entries would be the number of days times the number of pressure times the number of temperatures, 24. Right, 3, 3, 12, 20, yeah, okay. And then if you do that, let's see, the sum of the block doesn't use that. Okay, so sum of the block is just add up all the entries in block 1, square, add up all the entries in block 2, divided by the number of treatments. That's 12. Sum of the square of the temperature is sum across all the rows, each row, 1, 2, all the way to J, squared, divided by the number of samples at one temperature. So that'd be like the number of days times the number of pressures, right, being 6, minus this correction factor. And I know I'm not deriving this math. I'm just saying I get to take the paper and this is what it says, okay? Sum of the squares of the pressure is going to look just like the temperature, except you're going down now. Temperature went across the rows, pressure went down the columns. So each of the columns, this is pressure 200 and 200, 225 and 225. Each of the ones connected together, divided by the number of samples and the pressure. So that'd be the number of days times the number of temperatures. So that'd be 6. The other was 8. Let's see. So then the sum of the square all is, let's see, each particular sample squared. Yeah, so this is day 1, 1, 1, 2, the next day. So this is each day. Yeah, all right, divided by the number of blocks, 2, minus this correction factor. All right, so let's see, then you can take and get each of the individual terms. So sum of the square total, sum of each sample squared minus correction factor, sum of the squares of the pressure temperature interaction is this all minus the pressure minus the temperature. Okay, and the sum of the square error then is the difference between all of them. So you can put all of this in an Excel spreadsheet. And let's see. And if you don't like my sloppy notes, let's see. How did I didn't show it down, but you've got. Oh, here it is down here. Oh, there it is. All right, so you've got the paper in here. This is from Lincoln University. Okay, and what they've done, you can see the same figure we have, the block, the error, the treatment, the total, and then they're showing you what the ANOVA table would look like generically. They didn't fill any numbers in, right? But we had the block, that was the day. We had treatment, remember, temperature, pressure, and the interaction, then the error, then the total. So, this row grows depending on how many treatments you had, whether you had 1, 2, 3, 4, okay? Alrighty, and then all those all those calculations that I have. Oh yeah, they got their little, they got their little format, right? Calculate the correction, calculate the total, calculate block, treatment, block, group, error, calculate all the mean squares, calculate the F's, determine the P's. Okay, yeah, that's what the ANOVA table does for you, right? This blob is what the two-way ANOVA in Excel does for you. This is what we'll do by hand, but it'll be in Excel too. So let's see. Again, these are the very same formulas that I had on my notes, just in a much neater format that you can actually read. So, everything. And in fact, it's actually telling you what to do too, which is nice. If you're not, if you can't quite look and say, what do you mean by the sum of the block total? Okay, square each block total, add the totals, divide by the number of treatments. It's very clear the steps you're doing. It's actually a very nice paper, I thought. Then it's got your steps here. Remember, your mean square was each of the sum of the squares divided by the degrees of freedom. So it's got that all nicely laid out. Then the F, remember the F for the treatment was the mean square of the treatment by the error. F for the block, mean square of the block divided by the error. Got all that. And then the P's. So let's see. So, and even if that's not enough, they've got a nice little example for you. Okay, so they've got 5 blocks, 5 different drivers, and their treatment is cars. So they've got 3 different cars, 5 different drivers, and they want to see, what is the performance of the cars different, but the background variable is the driver. And I don't know what this is. It's made up data, but if it's gas mileage, these are what? Bugattis and Lamborghinis, it's not Toyotas and things. Because even my 69 Camaro doesn't get that bad. So, but I know that the Bugattis and things do. Sometimes maybe they're always like, gallons per mile sometimes in those things. So anyway, so you got 3 different cars that have some sort of performance value and 5 different drivers that are your blocks. So they go through all this example, calculating each of those numbers and show you how to use this. Let's see. There's some things I can point out. Yeah, a couple of things I can point out. So you can see, first, mathematically, this isn't that hard. You can see why I can do this by hand in an Excel in an hour and hand it out to you. It's not like it look, add up all the entries, okay, and divide by, and square them and divide by n, okay, let's see. In fact, they show some of the, like calculating the block, they show each of the steps, minus that was the correction factor here, right, so that was that. So mathematically, this is not that challenging. It's just making sure you keep your things straight. And so what do I do when I program this in Excel? I program an example that's here, and then when it works, I say, okay, I got it. Now I put my data in. Okay, so let's see. And so other points. Remember the F's. The F's are always the mean square of whatever it is you're asking about divided by the mean square of the error. And so let's see. Just right offhand, looking at these F's, they're pretty big, right? Because remember, F of 1 is F of 1 would say that the treatment and the error are the same magnitude. So if my treatment has a big effect, an F of 2 and F of 20, well, we know we're way out there. So just right offhand, before we even made any P calculations or looked at any F criticals, that one we sure much would think matters, and that would maybe depending on how many degrees of freedom and things like that. So let's look and see. So we've got now organized in the tables the degrees of freedom, the sum of the square errors as they calculated with their little formulas, mean square errors, again just this divided by that type of things. This divided by that, right? That divided by that, and that divided by that, and then the F's are that divided by that, and that divided by that. And then P, okay, yeah, where do they get the P's? Well, let's see. I'll state it, then I'll write it on the board. This P would be the distribution, F dot dist right tail, at this F with that degree of freedom for the numerator that degree of freedom for the denominator. All right, so let's see. I've got that written here, so that I don't make a mistake for you. Yeah, where's the P's? So, get 10 uprights. How can I write it purple? That's right, the P's there. All right, so let's see. So the first one, so let's see. P1 equals F dot dist, right, dot right tail. The dist gives us a P of 2.65, 4, and 14. Just remember that's the F value. That's the DF in the numerator. That's the DF in the denominator. Numerator, denominator, F. And that P, let's see. This said not significant. If you calculate that, it's 0.078. They should have written it in there, shouldn't they? So do you see why they're saying not significant? Because they're comparing it to what? They're comparing it either to 5% or to 1%, but which either comparison they make it to, that's bigger. Okay, so that F, the 2.65 or 2.64 was bigger than 1, but it didn't cut the mustard at the 1% level, did it? That's probably, who knows? I mean, I should have done the inverse. Well, it's close, close to the 5% level, but yeah, okay. And then the next P, P2, F dot dist, right tail, again, right tail, because we just want this right part of, not 2.65, but 20.6, okay, that's a monster, and then 2 and 14. 2 is the numerator degrees of freedom. 14 or 8. No, it should have been 8, shouldn't it? Yeah. Yeah. No. Let's make sure. Well, I tell you what, because my numbers are for 14, I'm sure. Speak up, man. Let me do that to you. Let's figure out what they are while we're here in class. I should have Excel already up. And that way you can see me do it too. So, let's see. The food's not here yet either, is it? There it is. Okay, good. There. Thank you. Okay, we'll get a blank one up. Let's close that. So now let's see. Let's put not put the right numbers in there. Doing. All right, so let's see. Blank. So let's see. We'll put the right. All right, so it should be equals F dot dist by tail. Yeah, that. But hey, I figured it out myself, right? 2.65, comma, 4 and 8. 8. So this is going to make it worse, right? Yeah. Right. 1, 2, 8. So let's see what this one is. See, I didn't write it down. You don't know I made a mistake.
0.00699.
Okay, so it's very, very low. Right, yeah. I had 0.000675. Yeah. So here I'll show you. So, right. So basically, it was 20.6 and a 2. 20. Whoops. 20.6, 2. What Bill's saying is it's extremely small. Yeah. Yeah, and so you see what, yeah. All right, let's get it. This is a good little spot, this is a good spot to start. So you see where that comes from, you see why they say it's not significant, or it is significant. Yeah, and you see how I made mistakes. See, you can make fun of me. He makes mistakes. Dang. I make them all the time.
Yeah, yeah. So pot 12